Okay, so yesterday you guys looked at this graph. This is actually called a logistic graph. I don't really know when you study them. It's not in pre-calculus or calculus. There's somewhere along the line that you'll study logistic graphs, but they always have this same basic shape, that something starts increasing kind of rapidly and then it levels back off, like the spread of the flu. All right, and so you all yesterday figured out the first derivative and second derivative at a whole lot of points. We found the maximum of the first derivative to be 11.454. And so at that point, the first derivative is 150.750. Did you guys find the second derivative there? Anybody have a chance to do that? It's 0, yes. All right, and so 4 says, for which value of t, or values of t, is f prime increasing? And so when you're looking at f prime increasing, you can look at the values. So it goes from 3 to 11 to 91 to 147. When do you think it's going to stop increasing? At the maximum, which is 11.454. All right, so we would say so what we're going to find is that the relationship between the first derivative and the function is the same as the relationship between the second derivative and the first derivative. And so if we wanted to tell how we know, we could actually look at the values of the second derivative. What do you notice about them in terms of positive and negative in that range? Positive, yeah. So we're going to say because f double prime is positive. Right, and then we can say something similar about decreasing. Well, thank you.
You're
welcome. This is a 21-day period. Yes, so we'll go to 21. Okay, now I want you guys to think back to pre-calculus. And we were actually talking about this today, we're just going back over it, about when a function, when the rate of change is increasing and decreasing. Do you guys remember the rule for concavity? Like when a graph is concave up, is the rate of change increasing or decreasing? Increasing. And when a function is concave down, the rate of change is decreasing. What is rate of change in terms of derivative? It's the slope. Like the first derivative is the rate of change. And so the first derivative should be increasing when the function is concave up and decreasing when the function is concave down. So we'll see again. So it says, how can you get your answer to 4? Just by looking at the graph of f. And you can do that using the concavity. When a function is concave up, f prime is increasing. All right, I'm going to give you the rest of the notes. I also want you, while I'm doing that, to look at your f double prime, your second derivative values when the function is concave up, and your second derivative values when the function is concave down. So that is another thing. We're going to learn a lot of different things today about concavity and the first and the second derivative and all that. But whenever the second derivative is positive, then this function is concave up. When the second derivative is negative, this function is concave down. So the original function. Okay, so let's look at we're going to come back to these two, hopefully, at the end of the lesson. All right, so we're going to analyze function behavior with the second derivative today. So the graph of f is concave upward on an interval whenever f prime is increasing. Now, I actually talked about this in pre-calculus today because some students were confused because they were looking at like this right here. So we'll say this, we would say like that slope would be about -1. This slope right here would be about -1/2. Is that increasing? Is -1/2 bigger than -1? 100%. So they were thinking steepness. That is not what it's saying. It's the value of the first derivative is increasing anytime it's concave up, and then it goes to 0, and then it like goes to 1, and then it goes to 2. So that value of the first derivative, or the value of the slope, is increasing anytime the function is concave up. All right, and all those little tangent lines I drew, the graph lies above all of the tangent lines on that interval. All right, and then we have the graph is concave downward on an interval when f prime is decreasing. All right, so we could draw little tangent lines, and you could see that the values of those slopes of those tangent lines are just getting smaller and smaller until we get to 0, and then they start becoming negative, which is getting smaller and smaller. And all those little tangent lines, the graph lies below them. If you draw a tangent line on concave down, it's going to be on top of the graph. Okay, so we have some tests for concavity. So f is a function whose second derivative exists on the interval if the second derivative is positive or greater than 0, then the graph of f is concave up on that interval. That second derivative is negative. The graph of f is concave down on that interval. Okay. And then last year we learned a little bit about points of inflection. Do you guys remember what they are? What a point of inflection is?
Concavity changes.
Very good. So the point at which the concavity changes is the point of inflection. Now, the point of inflection, the function must be continuous on the interval, and the tangent line must exist on that interval. It is okay for the tangent line to be vertical, or slanted, or horizontal, but the tangent line must exist. Great. So if we have a point of inflection at C, then either the second derivative at C is 0, or the second derivative is undefined. Very similar to a critical number with the first derivative. All right, and so if we're checking for points of inflection, I don't have that up here, but the second derivative will change sign. So the second derivative will change from positive to negative, or negative to positive, and we'll practice that on the back. I know this is a lot of information. Hopefully some of it sounds a little familiar because of what you learned in pre-calculus last year. Okay, and then the second derivative test. Most people prefer the first derivative test. It actually sometimes just makes more sense, But sometimes you have to do the second derivative test because of the information that you're given. And so the second derivative test says that f is a function and f prime of c is 0. What does that mean that c is from previous lessons? If the first derivative is 0, what is that going to be? It's a constant. Oh, the slope is constant, yeah. But what is c called? It's okay. I don't like to play guess what I'm thinking. It's a critical number. So c is a critical number. And the second derivative exists on that interval containing c. If f double prime of c, so you plug c into the second derivative and you get a positive, does that mean that the graph is concave up or down? The second derivative is positive. Concave up. Is c going to be a relative max or min? Min. C has a relative minimum. At that point. So c is a critical number, that's important. And the second derivative at c is positive. We have relative min. All right, same thing. C is a critical number, which means a potential relative max or min. This time, the second derivative at c is negative. So what are you going to have? Relative maximum. At that point. All right, and then if it's a critical number, but when you plug it into the second derivative, you get 0, then the test fails. You can't get anything conclusive from the test, and so you would have to use the first derivative test instead. All right, y'all ready to do all the things? Yeah. All right, so on example 1a, we're going to find where this polynomial function is increasing or decreasing. All right, what do we need? Always the derivative. From this derivative, we need the critical numbers. I'm going to keep factoring this. We can find the critical numbers without factoring it, but it'll make it a little easier for us later if we factor it. Yay. You guys used to be good at factoring, I think. Maybe we didn't practice it enough last year.
Throw a constant in front of it though, and I'm screwed.
Oh, we gotta get better than that. Okay, so we need to know if we're doing intervals of increasing and decreasing of f, we need to know if the first derivative is positive or negative. Why am I putting 3 parentheses here? Yeah, there's 3 factors. This first one, no matter what I put in for x squared, it's going to be positive, right? And then when I multiply that by a negative 15, this is always going to be a negative. All right, so here we go. Let's plug in a number that is less than -1, so like -2. Put it in for both of these. That's going to be all negatives. All right. Now, we're going to have to plug in some fractions or decimals. That's okay. If I put in a negative 1/2 and I add 1 to it, that is a positive. And then if I put in a negative 1/2 and subtract 1, that's a negative. It happens again. All right, and then something bigger than 1. Right, and then if you guys want to, you can draw the little arrows that show the direction. That's up to you. But when the first derivative is negative, I know the function is decreasing, increasing, increasing, decreasing. I do know this is a polynomial function, and the polynomial function is continuous and differentiable everywhere. So when I do my interval of increasing, I go all the way from -1 to 1. Okay, so I hope you guys are good at that. You definitely had to do that on your quiz yesterday. Okay, part B tells us to find the relative extrema. So it looks like this is going to have one relative maximum and one relative minimum. And we'll start with the min since it happens first. So anytime the first derivative changes from negative to positive, we have a relative minimum. And that's going to be when x is -1. All right, and then we would need to plug that -1 into the original function. Which means we're going to raise it to the 5th power, which keeps it -1. Multiply it by -3, which is +3. Raise it to the 3rd power, which keeps it -1. And then multiply it by 5, so that would be 3 minus 5, or -2. And then f is going to have a relative maximum when x is 1. And plugging in 1 is awesome. Almost as easy as plugging in 0. But plugging in 1, you just add the coefficients. Oops. But add them correctly. Okay. So we have our two relative extrema. Y'all good? Oh, that's okay. You didn't have to find the y value on the quiz. You just had to find the x value on the quiz.
I'm putting x equals and I was like.
It's okay. That's what I asked you to because I didn't want it to take forever. All right, and then we're going to state the intervals where the graph is concave up and concave down. That's new today. So what do I need to decide concavity? Second derivative. I'm wondering if I have enough room down here. We'll make it work. Okay. So second derivative, we'll go back to the first derivative in dark blue up there. Let's go ahead and do it up here. We'll do it in light blue. All right, so we'll just multiply by 4, take 1 away, multiply by 2, take 1 away. And so just like the critical numbers for the potential relative maximum and minimum values, we need to find when this is 0 for a potential point of inflection. Or, no, sorry, just kidding. We need to know where the concavity could change, or it is a potential point of inflection. So let's plug it equal to 0. I'm going to, just to save on room, I'm going to go ahead and factor out a common factor of negative 30x. You can factor out positive 30x if you want to. All right, so here we go. We're going to want to know the sign of the second derivative. Now, on a fraction, you can take the, if it's the square root of a fraction, you can take the square root of the numerator, which in this case would just be 1. And then that denominator, I'll just leave the square root of 2. That might help you when you're trying to find numbers to test. Okay. So do you guys know about what the square root of 2 is? It's 1 point something, like 1.4? 1 point something. So it's between 1 and 2. So if I take 1 and I divide it by something between 1 and 2, would 1 be bigger than that? Yes. So it's safe to put -1 in here. If you don't want to think that much, put in -5. It's fine, whatever. So I'm going to put -1 in for this x, which is going to be -30 times negative. It's going to be a positive. When I put it here, I'm going to square it, so it's going to be 2 minus 1, which is a positive. Now this is where it gets tricky. We want to pick a fraction or a decimal that is between -1 over the square root of 2 and 0. What do y'all think? The absolute value of this fraction needs to be less than 1 divided by 1.4. So it could be 1 divided by any number bigger than 1.4. All right, so something would be 1 over 2 or 1 over 3 or whatever, it doesn't matter. All right, so all I need to know is positive or negative. So when I multiply that by, I multiply -1/2, sorry. By -30, it's positive. When I square it, it's 1/4. And then I multiply it by 2, it's 1/2. And then I subtract 1 from it, that's going to be a negative. They're not all this annoying, just so you know. All right, and then same thing for f double prime, I can plug in 1/2. And a positive times a negative is a negative. The very exact same thing is going to happen when I put it in here. So that's going to be another negative, which will multiply to a positive. All right, and then I'll put in 1, and I can just go back, if I wanted to, go back to the original and add the coefficients. -60 plus 30 is going to be a negative. All right, so now I have what I need to answer this question. So f is going to be concave up anytime that this second derivative is positive, which is from -infinity to -1 over the square root of 2. We'll do a bracket. And then between 0 and 1 over the square root of 2. Alright, and then f is concave down when the second derivative is negative. So through doing that, we have found the x coordinates of our points of inflection, which is D is asking for the whole points of the point of inflection. Trying to figure out where to put this. Okay, so D. So anytime the second derivative changes sign, there is a point of inflection. So it looks like there's going to be 3 points of inflection because we change sign every time. And looking at my answers, I just used the calculator to find the y coordinates here, except on 0. Okay, so I hope you guys have some more room because we have one more thing to do, and it's to draw the graph. So we can get a pretty awesome graph without a calculator at all. Like, we haven't touched a calculator this whole time. I did. I touched a calculator here. But it's still going to be a good graph. All right, so on the x, I think we only need to go over to -1 and 1, but we can go farther if we need to, if you want to. And then our relative max was at 2, so that should be the highest we need to go, and min is at -2. So I'm going to go ahead and graph my relative maximum, my relative minimum, my points of inflection, and then I can just look at like increasing, decreasing, concave up, concave down to get all my things. So when the graph starts becoming a graph at -infinity, is the graph increasing or decreasing? Decreasing. Is the graph concave up or concave down? Concave up. So I can pretty much know that from the beginning of the graph until I get to that minimum, that the graph is decreasing and concave up. So it's going to look something like that. All right, and then from the minimum to the point of inflection, we should be increasing. Are we still concave up? Yes. Oh wait, 0, is 0, 0 anything special? It's also a point of inflection. I missed it, sorry. Okay, and so from this point of inflection to the next point of inflection, we're concave down, and we are still increasing, right? Yeah, we increase all the way to 1. So concave down and increasing, boom. Right, so we are going to increase all the way to that maximum, but concavity is going to change. So between those points of inflection, we're up. And then for the rest of the graph, we're concave down. So we're increasing to the maximum and then decreasing. Isn't that fun? You guys know so much. It's so much fun. Liam's like, I don't know if I'd say fun. Okay. I'm going to do this exam. I think we'll finish. I wanted you all to have a little bit of time, but the next 2 should go pretty fast. All right, so for example 2, it says we have the first derivative. We're going to use the second derivative test to find the x-coordinates of any relative extrema. We don't have the original function. Are you stretching or you have a question? Stretching? Okay. So we're going to use second derivative test. So obviously we need the second derivative. Oh, we need something from f that I skipped over. So to do the second derivative test, you have to have the critical numbers that come from what makes that first derivative 0. That is important. So it helps me to remember that critical numbers using the first derivative are always potential relative maximum and minimum. That's why you find them. And so now that I have them, they're potential, we can figure out if they're actually relative maximum, relative minimum values by plugging them into the second derivative. And all we really need to know is if we get a positive or a negative. So we could actually do it all out if you wanted to. Or just use logic. So if I do that, am I going to get a positive or a negative? Definitely a negative. Negative something. It doesn't matter what. All right, so that means we have a potential relative maximum minimum. The second derivative is negative, so we're concave down. So what do we have at -2? Maximum. All right, when I plug in 4 to the second derivative, I definitely get a positive. All right, and if you need to go through it every time, it's fine. Positive means concave up. Concave up. If you draw it with your hands or your mind, that's definitely a relative minimum. All right, so let's do B real quick. What's my critical number going to be? Yeah. So you just think about what's going to make that 0. It's definitely -3. Or set it equal to 0, whatever you need. Oh, well. Get ahead of myself. Oh. Second derivative is always 3. So what does that mean x equals -3 would be? Concave up, so yes. Sorry guys, you're not going to have much time to work. I'll give you a little extra time to do your assignment. You need to practice some of it though over the weekend because what we do on Monday, you'll be completely lost if you haven't practiced this. I don't want you to be completely lost. Okay, so on the back of the flu paper, that sounds gross, there's a couple of more questions, and I love these questions. This is what you might see on the AP exam multiple choice. So we have this graph of f. So we're talking about f here. Determine all the intervals where the first derivative is positive and the second derivative is negative. So the first derivative is positive. What does that mean about the graph of f? Increasing. The second derivative is negative. What does that mean about the graph of f? Nice job. Okay, So what are the intervals where that happens? Increasing and concave down. Yes, ma'am. It does say to justify. Let's just say because f of x is increasing and concave down. I'm not sure that's a great justification. You probably would need to go into more detail. First derivative is positive, so f of x is increasing. Second derivative is negative, so f of x is concave down. Okay, and then for this one, for a twice differentiable function h, it is known that h prime of 3 is 0, and h double prime of 3 is negative 1.5. Which of the following statements could be false? So, is it true that h is concave down at that point x equals 3? That is true. Is it true that h has a critical point there? Yes, that's what this means. Right? Do we know if h has at least one point of inflection? We do not know that. That's probably the answer to the question. Do we know that h has a relative maximum at 3? Second derivative test. This is a critical number. This is less than 0. This is negative. That means we're concave down at a critical point. Then it's a relative maximum. All right. What questions do you guys have? It's marathon day today. Okay. I am going to give you more time to get this done. But like I said, it will be helpful if you have it. If we're doing an activity and nobody knows anything, and the activity is going to be tough. It's nothing stressful. Elijah, I'm sitting here back on this row. Do you want to come today, Elijah, and take your quiz during homeroom, or do you? Sure. Okay. Oh, where are my passes? I've got to do some cleaning. Sorry. How picky is Mr. Harnden about passes? You just have to have one. Doesn't have to be purple. Oh, wait. No. You just pretend when you say just. I will.
Sometimes you know it's fun.
Sometimes.
Sometimes.
Sometimes, and then I get lost.